All right, 3.1, we finally made it through chapters 2. Long lectures. So 3.1, we kind of venture back into linear models or linear functions, which is just another way of saying lines. So a linear function is a function of the form f of x is equal to mx plus b. The graph of a linear function is a line with a slope of m and a y-intercept of b. And then we already know that the domain of all linear functions is going to be all real numbers, or in interval notation, negative infinity to infinity. So just a quick refresher again, if we were asked to graph the following line, we know that 5 or 0, 5 is our y-intercept, so we can place that down. And then we can use the slope, right, negative 2 over 3 to find another point on that line. So I can go down 2 to the right 3, 1, 2, 3. Or we can go up 2 and then left 3, 1, 2, 3, right? And then our line would look something like this. Okay. So the main idea to take from this is this next theorem about average rate of change. So an average rate of change of a linear function is constant. So because it's not, if you look at it, it's as you go from one point to the next, it's changing the same ratio. So linear functions have a constant rate of change. That is the average rate of change of a linear function. Again, a linear function f of x equals mx plus b is given by the change in y over the change of x, which is a fancy way of just saying the slope. So the main thing that we can see is that if our slope is changing at a consistent number, we can use it to identify that we actually have a linear function, right? So then if you give us a chart, something like this, in example number 2, we can determine whether the function is linear or not. Okay, but before I get into this particular example, let me kind of explain what I mean by how do we know whether or not this function is linear. So for instance, if I were to continue this process, right, let me back up this line real quick. Okay, so let's say I continue this slope process of going down 2 and to the left 3, 1, 2, 3, right? And I create a quick XY chart of these points. Well, of course, we have 0, 5. We have 3, 3 by looking at our graph. We also have 6, 1. And then the other one I threw up there was negative 3, 7, right? So we already know, of course, this is a linear equation. I've already graphed it for you. We know it's a line. So what I'm saying is now we're going to be looking at a table of values and determining, hey, is this thing linear or not? And we can do that by looking at the slope between points and seeing that they're the same exact number. It's constant. So what I mean by that is what we're about to do in this table below is I'm going to say find the slope between these 2 points, which is basically, again, looking at 0, 5 and 3, 3. Right? Remember, the slope between 2 points can be found by y2 minus y1 over x2 minus x1. So we just have to label them. So if I label this x1, y1, this guy x2, y2, of course, we shouldn't be shocked that our slope should be negative 2 over 3 because we already know that's here. I'm just showing you the process here. So if I found the slope, it'd be 3 minus 5 over 3 minus 0, negative 2 over 3. So my slope, negative 2 over 3. And if I did it again for this set of points, or these sets of points, if I look at 3, 3, and 6, 1, label them again, plug into my formula, y2 minus y1 over x2 minus x1, negative 2 over 3. And see, each time, and I'm guessing you would know this, we'd get another negative 2 over 3. So if we're looking at a function in terms of its xy points, and we find the slopes between them, and they have to be this same consistent number, this constant number here, we know that what we're dealing with is a linear function. So that's what they're asking us to do in example 2 here. So they're saying find the average rate of change, find delta y over delta x, and determine whether or not it's linear. And that's just basically they want you to know, is the slope coming out the same or consistent every single time? Okay, so if we wanted to find the slope between these 2 points, right, let me do that on the side here, just to keep our notation the same from previously, negative 2, 4, and the other point is negative 1, 1. If I look at the slope between those 2 points, label them x1, y1, x2, y2, it would end up becoming y2 minus y1 all over x2 minus x1. So this becomes -3 over +1. So that equals -3. Okay, now if you find the slope between the next 2 points, let's say -1, 1, and the other one is 0, -2, x1, y1, x2, y2. Okay, so then your slope would be y2, said it right that time, y2 minus y1 over x2, which was 0, minus x1. So this becomes -3 again over 0 minus a -1 becomes a +1. So this becomes -3. So let's do this one more time to convince ourselves. If you do the next 2 points, what was this? 0, -2, and 1, -5. Again, if I label them, substitute into my formula, y2 minus y1, watch out for those negatives, over x2 minus x1. -5 plus 2 is -3 over 1. Right, so we kind of notice that we have this consistency here. And notice that this guy must be linear. Now, we say, since the slope is coming out to be -3 every single time, we say this guy is linear for sure. Now it says, this next part of the question says, if it's linear, determine the equation of the line. Well, if it's linear, it should fit the model y equals mx plus b. The good thing is, we found the slope. Our slope is -3, and we actually have our b is the y-intercept, which is, notice, remember y-intercepts are found when x is 0? They kind of give us the point right here. If I plug in 0 for x, my y value is -2. So that's my b value right here. So maybe I should highlight that in blue and show you where I got that from. Okay, and that's it for that problem. Now, the next one, do the same exact thing. So here we go. If I'm finding the slope between these 2 points, we're going to get, let's see, let me underline this real quick to give me some room here. Okay, so we have the points -1, 64, and the points 0, 16. So this is x1, y1, x2, y2. Our slope is found by 16 minus, my pen stopped writing, 16 minus 64, come on. There it goes. 64 all over 0 minus a -1. So you have 16 minus 64, which is going to give us -48. And then 0 minus a -1 is giving me a +1. So our slope is -48 between those 2 points. Okay, now if we do the next set, we'd have the point 0, 16 and the points 1, 4, x1, y1, x2, y2, y2 minus y1 over x2 minus x1. And notice really quickly, this is not going to be the same number here. So automatically, we don't even have to do anything else. We can already say not linear. Right, so all I wanted you to notice is that linear functions have a constant average rate of change, right? Because it's basically the slope. That's all they're trying to point out to you. And that's how you can tell by given a chart of values. So if an average rate of change of a function is some constant n, a linear function can be used to model the relationship between the following variables. So all they're saying, they're going to put some new notation here just because we know what function notation looks like. Instead of saying y equals mx plus b, they're just saying f of x equals mx plus b, where b is the y-intercept, or the value of f of x evaluated at 0. That's how your book describes it. Now, all that's telling you is that when you substitute in 0 for x, your b value is what the value of the function is, right? Which we already know, if you plug in 0 for x, that's the y-intercept. So nothing's really changing here. The main purpose is for you to be able to notice linear models based on that, and that's what example 3 is. You notice that in the notes we're skipping 3.2 because 3.2 kind of is already involved with 3.1, and this is a perfect example of this. So this is our last example, easy, short, first section of chapter 3. So it says build a linear model from the verbal description. So suppose that a company just purchased a new office equipment and it costs $2,500 per machine. The company chooses to depreciate each machine using a straight line method. So they're just telling you, hey, we need you to find an equation of a line that represents this thing, straight line method, over the course of 5 years. This means that each piece of equipment will depreciate by $500 per year. So part A just says build a linear model that expresses the value V of each machine as a function of its age X. Okay, so the better you understand how we come up with these models, the easier the transition to calculus will be as well. So first of all, they want us to come up with a function, and basically function value V related to its age X. So basically that's telling us for part A, they want V of X, some function, to be equal blank X plus blank here, right? And it's supposed to fit this idea of the straight line form, y equals mx plus b, or getting used to function notation, f of x equals mx plus b. So the first thing we have to realize is that two things. X is representing the years after purchase, right? That's what the variable stands for. So if you were to substitute in 0, that means that's the year that you just purchased it, so year 0. If you substitute in 1, then you're substituting in 1 year after you purchase it, and it wants you to be able to come up with that function value. Okay, so then that gets us into what the heck does V of X really represent? So V of X is the value of the machine X years after purchasing. Okay, so first of all, one thing to realize is this. We should note, as we're trying to develop this model, if you were to substitute in 0 for X, right, that's 0 years, that means you just purchased it, which means it should be worth 2,500, which means that if that's the function evaluated at 0, that's also your y-intercept, which means that 2,500 comes here. But if it's depreciating at a rate of $500 per year, then your slope would be 500. But you got to be careful here is that it's depreciating from that 2,500 mark, so this slope should actually be negative. So now we have our function for part A. Now the next question says, what is the implied domain of the function found in part A? So of course, if we look at the implied domain, we know that the domain of all lines are negative infinity to infinity, but we have an implied domain because we're talking about this particular type of problem. So remember, X is standing for years after purchase, so obviously it wouldn't make sense for X to be negative, because then we talk about negative years before you purchase it, right? We're not considering, years before you thought about purchasing this thing. So obviously your implied domain, D, is going to start at 0, and then it's going to depreciate over the next 5 years, right? Which makes sense because after 5 years, it's basically going to be worthless, right? Notice that if you substitute in 5 in for X here, 5 times 500 is 2,500, and then obviously it's worth nothing after the 5 years. So your implied domain is from 0 to 5. Now it says graph the linear function. Now it's going to be hard. Obviously, we have huge numbers here. But let me just give an idea of what this looks like. So for part C here, all you're basically doing is noticing that, hey, you have a y-intercept at 2,500. 5 years later, it's going to touch the x-axis, right? Because it's going to be worth nothing. And then you're just drawing a line that looks something like this. Okay, so we know it's a line. We know that the slope would be negative, so it should be going down as you go from left to right. Part D says, what is the value of the machine after 2 years? So this is why knowing what each of the variables stand for that we wrote up here is very important. Because in D it says, what is the value of the machine after 2 years? So basically they're just asking you to, once you have your function, v of x is equal to negative 500x plus 2500, they just want you to substitute in 2 for x. So sub x equals 2 because it's 2 years after you've purchased it. So v of 2 is equal to negative 500 times by 2 plus 2500. Of course, that would just be 1000 plus 2500 would leave us with just 1500. Right, so what is the value of each machine after 2 years? 25, I don't know why that looks like a 2, $2,500. So then it's saying interpret the slope. Well, what does the slope represent? Well, we kind of talked about that when we developed this in general. We know it's the rate of decrease of each machine, right? Because it's depreciating $500 per year. So we can say this is the rate of decrease in value of each machine. In value of each machine. And now part F. Part F says, when will the value of the machine be $500? So we could have also made I'll make a quick table of this to show you, okay, we could have just thought about this without using all of these models. But the idea is that we're going to be able to build these models in calc as well. So you're just going to get used to it here. So when will the value of each machine be $500? So again, you're given v of x, or sorry, we found v of x to be this function here. If we want to know the value when the value will be $500, that means that they're telling you that v of x is equal to 500. They want you to find x, right? Because x represents years after the purchase. So how many years will the machines be worth at least just $500? So this piece is 500, the whole thing, that's the value. And you're trying to figure out, well, when is this thing going to be worth just $500? So if we solve for x, subtract 2500, you get 2000 is equal to negative 500x. Negative 2000. You divide by 500 and you'd get 4. So when will machines be worth $500? For 4 years later, after you purchase them. After purchase. Okay, now we could have done this just by a table of values, understanding what the question is asking for, right? But obviously they're not always going to be this easy. Not everything's going to be modeled by a straight line, right? So what I mean by that is we could have literally just done this. Here's x, here's y, right? Or here, let's just be more consistent with the problem. Here's x, here's v of x, right? We know at year 0 it's worth 2,500, and every year it depreciates by $500. So after year 1, it's only going to be worth 2,000. Year 2, it's going to be worth 1,500. Year 3, 1,000. 4, 500. Again, year 5, worth nothing. So again, we could have answered most of these questions. The implied domain, of course, we're only going from 0 to 5. Graph it, that would have gave us some nice points here. We could have graphed this point here and this point here, the x and y intercept, and called it a day. What is the value after 2 years? If I look at part D here, value after 2 years, 1,500. Interpret the slope. So that would require you to find the slope, but we already know that it's depreciating by 500, so that part was easy. When will the machine be worth $500? Well, then all you're doing is looking at the value, which is v of x, at 500 and saying, oh, yeah, that's 4 years. So, of course, if you would have just made a table of values, it would have been fine, but obviously these numbers worked out really nice. So all you want to be able to do is recognize when you have a linear equation or a linear function, and you would do that by noticing that the average rate of change is just constant, right? Which is the slope of that particular line. Good thing is now 3.1 is out of the way. I know we kind of traveled backwards to talk about lines again, but now we're going to travel into quadratics and 3.3.